Hello again, everybody, and welcome back. Continuing chapter 5 on Newton's laws and forces. In this segment, I'm actually going to define two forces. First of which is going to be friction, and then tension will be after that. And then my goal is to do one example. So the next chapter after this is going to deal more with friction. Here we're simply going to just define friction as, you might just say, a force that is to be dealt with. We did a problem earlier on, I think, with a fireman, where the fireman slides down a pole and depends on friction to slow him down. But next chapter we're actually going to calculate it and make measurements on friction. Right now we're just simply going to state that friction exists. So what is friction? Well, it's a force that opposes any motion between two surfaces. No matter how smooth a surface may seem, on a microscopic scale, that surface has little hills and valleys, little ridges in it that make it not all that smooth. And so two surfaces touching each other, two imperfect surfaces like this, have lots of millions and millions of little hills and valleys that actually catch on each other when you try to slide them past one another. So what that means is that this object, see the top object, the wooden block right here, is attempting to move that way, all right? You might say that's the acceleration, that's the force moving that way, the applied force. And so friction is going to, the friction between I probably should have written that in green, that would have made more sense. So green for go, right? I'll get my green up right here. So here's our applied force, not very visible, but you can see it. And then the friction force, I'm going to call it, for the time being, I'm going to call it FR, and I'm writing it in a lowercase f, that is this F right here, because it's not really an active force. It's a reactive force. It opposes motion. So if we're trying to move our wooden block towards the right, then friction between the block and glass, and even glass is somewhat smooth, FR, the force of friction, is going to act in the opposite direction. Right, because these little hills are trying to move over the bottom hills right here, and so friction slows it down. Just like if this force were to be applied towards the left, then friction will be acting towards the right. So friction only holds you back. It only slows down, or I shouldn't say slows down, but it acts against applied forces. Again, next chapter we're going to talk about it in a little more detail, but it's simply a force to be reckoned with. So whatever your force is, whatever the attempted motion is, then friction is going to be acting in the opposite direction. Most people think of friction as being a bad thing, like it slows you down, it makes things hard, but it also is a good thing as well, because friction is what keeps your car on the road. It's what helps you to walk. You pushing backwards on the ground with your feet allows you to propel your body forward, all because of friction. If everything were frictionless, we'd be sliding all over the place and it would be no fun. So friction can be a good thing as well, but friction is simply a force that acts against an attempted motion. I drew little diagrams on the next little slide here, sort of illustrated already, but again, if our applied force right there is going that way, then friction, and I usually try to draw friction as being close to the two surfaces, F our force of friction is acting against it. Similarly, in fact, that's all I read up. I'm going to do right there. There's a force of friction. Now, friction doesn't act unless it's acted against. So if a box is just sitting here, just pretend I didn't draw that red arrow for a second, but if it's just sitting there, friction is not going to act, but it only acts if there is some sort of attempted acceleration. And of course, we know an acceleration is a result of a force being applied. So whatever direction the force is being applied, friction will act against that. Force is applied this way, friction acts against that as well. But friction doesn't act unless it doesn't act if there is no force applied. So that's friction, and we're going to have to deal with that. It's a force going to be acting against our attempted motion. The second force that we're going to talk about is similar to a force that we've discussed already in previous problems. You may mention the idea of the contact force, and how two boxes that are touching each other, if you apply a force to the one box, it's going to cause the second box to move because it's touching the first one, that contact force. Tension is kind of like contact force, and I'll try to illustrate that in just a second on the next slide. Tension is a force exerted between strings or ropes or maybe chains. that keep the string the same length. Now, what I mean by the same length is that don't think of tension as being like a rubber band. You can attach a rubber band to something. All right, let's draw a little box right here. If you attach a rubber band to something and then do a red rubber band, all right, and you pull it, the rubber band will actually stretch to a different length, and at some point it might actually pull your box. We're actually doing work. We're actually wasting some energy, wasting some force, stretching that rubber band. We'll deal with that later when we get to springs, but it's not a stretchy object. It's simply something that has the same length. So a string, a chain, a rope, all those have a constant length. And so if I have my box right here and a rope applied to it, the tension in that rope is going to be a force that acts much like a contact force that acts in two directions. So I'll put an arrow on this end and on this end right there. We call that T tension, and it acts in both directions much like a contact force. Now the interesting thing about tension, at least in ropes, is that it can only pull. You really can't push a rope, can you? Again, I'll illustrate that in just a second as well. But it can only pull, so you can't push with a rope. Thirdly, I'm sorry, that was third. I missed one. That was the third one. The second one I missed. For our purposes, we're going to assume the ropes and strings and chains even to be massless. We know in the real world they have mass, and many chains, especially the big ones, can be very, very massive. Well, in our problems, we're going to assume the strings and ropes to be massless, almost as if they're ideal tension instruments. Okay, so that's one good thing. We're going to ignore the mass of them, much like we ignore things like air resistance and that kind of thing. All right, but we're ignoring mass. We talked about how tension can only pull. Fourthly, it pulls with exactly the right amount of force. Let me illustrate it this way. If you have a box right here, all right, and you apply a tension force to it. Say that tension force is, 5 newtons. That 5 newtons acts all along the length of that string right there, such that a tug is felt to the tune of 5 newtons down here as well. If you applied a 5 newton force to the end of a rope, but somehow the rope was able to apply 6 newtons to the end right here, first of all, I can't even picture that in my head, but you'd be somehow getting work, you'd be getting force out of nothing. All right. So the idea with the exactly right amount of force is whatever tension you apply to the end of a rope, that tension is the same all through the rope down to whatever object you're applying. You're applying the force to. All right. And lastly, at some point we're going to be dealing with pulleys. All right. Now, here's a pulley right here, and pulleys are kind of interesting because you know that pulleys can do strings, rope, chains, that kind of thing. Well, let's just say right here we have a mass. All right, I don't know what the mass is, but it's attached, and it's not very straight right here, but it's attached kind of on the corner like that. It's attached, and it goes over. It goes over a pulley and down to another, say, it's supposed to be a smaller mass right there. Okay. Mg, I'll call that M1G, mass 1, and I should have made this a little bit bigger, but mass 2, we're going to call that mass 2G right here. Well, what's going to happen if you have a greater mass, and then we've got tension in the string that wraps around a pulley right here, down to a lesser mass? Well, what happens is that there is tension all along this rope, but what the pulley does is it wraps that force around a corner. You can bend a force around a corner with a pulley, and that's what the purpose of pulleys is. They change the direction of tension, and we'll talk about this thing. This is actually called an Atwood machine that we'll discuss a little bit later. We will deal with connected objects like this later, but there's a force from this mass, the weight force of this pulling down. There's less of a weight force of this pulling down right here. So what's probably going to happen is that this whole system is going to rotate that way. Okay, so here we would call, if it's rotating, say, counterclockwise, this direction downwards would be, we'll say, positive. All right, I'll do a little positive this way, positive that way, or negative that way. So if this direction downward is positive, then that means this direction downwards is negative right here. And so you have a positive, negative coordinate system. It's simply wrapped around a pulley. And that's what the purpose of pulleys is. Okay? So, let me illustrate something here on the next slide. So I've got four sets of boxes. And I'm going to illustrate, sort of to recap, some of the forces between items that exist. We talked about before the idea of the contact force. All right, a contact force only exists between boxes if you apply an outside force. So I'm going to apply, let's see, an outside force of 7 newtons. I should put an F right there. Force equals 7 newtons. And so that means there's going to be, if I call this box 1 and this box 2 right here, even though I'm only applying a force to box 1, there's going to be a contact force between box 1 and box 2. So that's force 1 to 2, and this is force 2 to 1, right? So it acts two different ways. And whatever that force is, that's the contact force between the boxes, it's the exact same in both directions. All right? We're not going to talk about this, but what if you had a contact force and you had an ideal massless, say, rigid rod in between the two boxes? Like maybe a glass rod or something like that, and let's just pretend it was massless. All right? Kind of like we're pretending rope is massless, right? Well, if you apply a force, say another 7 Newton force right here, force equals 7 newtons, you've got really a contact force. Oops, I'll make this it's a different color. I'll make it, well, since I'm using teal, no, that won't show up very well. I'll use blue. So that is not right, sorry, right in here. So you've got a contact force between box 1 and this kind of ideal rigid rod, and you've got a contact force between the rigid rod and box 2 right here. So it goes, I did it again. I meant to draw it the other way. Sorry. So that's force from 1 to the rod, and this is the force from rod to 1. And we got it this way too. Force from the rod to 2, and force from 2 to the rod. Okay? These are really all just contact forces in here, but this rod is actually exhibiting a force called compression. We're not going to talk about compression very much, but think of it as just being another object that is applying a contact force between the first two objects. And so, box 1 and box 2 are moving in exactly the same way that box 2 and 1 are over here. It's just sort of like an extended contact force. All right? And again, try not to think of this as another object. It's just sort of an ideal rigid rod that applies a contact force all through the length. We call that compression. But what if you were to substitute that rod with a rope? All right? A rope. What would happen if you had this force right here, the 7 Newton force? Oh, you know what? I should label that compression. Okay? The rod is being compressed. But what if you have a rope in between? You apply a 7 Newton contact force. 7 newtons, and you've got a rope in between box 1 and box 2. All right, 1 and 2 right here. Well, what's going to happen? A rope can't, it'll compress, but it'll just kind of get wavy, right? It'll just do that, and it'll just sort of go slack, and you're not going to have any force applied from box 1 to box 2 because this can't apply compression. All right, so this is all just great big sad face right here. All right, because you can't have force being transferred through a rope that can just kind of crinkle up and go limp. But what you can do is this. If you have a rope between boxes, box 1, oops, I should make that a different color, make this orange. Box 1 and box 2, and you've got a rope between them, and you have a force applied to box 2. The force equals 7 newtons right here. You've got a rope between them. Then the rope will go taut, or that is, it'll go tight. All right, and so you will now have a force between box 2 and the rope, and then between the rope and box 1, and so the whole system will move. So much like up here, how the whole system is going to be moving because of the 7 Newton force, same whole system is going to be moving right here because of the 7 Newton force, but simply it's because of what we call tension. Let me get kind of a different color right here, sort of a darker green. Oh, I'm sorry, maybe like a darker, I'll just use red. All right, you've got, let's say, force of tension that way between 2 and the rope. And you get the force of tension that way between 1 and the rope as well. So tension, just like contact force, acts in 2 different directions, and it connects objects that aren't actually touching, like when they're contacted. But it has to be tension. I'll write this in orange right here. Tension allows this. You cannot have compression of a rope like you can have compression of a rigid rod, but you can have tension of a rope. And if you can just think of it that way, it acts a lot like a contact force. Tension acts both ways along the length of the rope in both directions, and applies whatever forces between 2 and the rope to box 1 down here, because the tension acts equally along the whole length of the rope. Okay? What I think I'm going to do, contrary to my goal, is I'm going to stop right here. I'm going to do the next example 510, in the next video segment. So that's going to deal with tension, and we're going to see how tension can actually be our friend, and then do more tension examples in subsequent videos. So thanks for following along. Please make sure if you have any questions to ask me, and I'll see you on the next one.